Okay, so today, like I said, we are going to start talking about imaging sequences and talking about the practical outcomes of MRI. Very cool stuff. As you can kind of see in this outline, we're talking about T2 weighted imaging and T1 weighted imaging primarily. And then near the end, I've got some diffusion weighted imaging stuff. Even as early or as late as yesterday, in my email, I mentioned we'd be talking about fMRI today. But when I was preparing this session, I got through diffusion weighted imaging and I was like, this is a lot of material. So I might just leave fMRI and ASL for next session, but we'll see. If we just like breeze through it and end up having a lot of time, we can touch on fMRI, but it may be left for next time. That being said, I guess off the top, next session, the kind of the last scheduled one in December on the 9th, all I really have planned is fMRI and ASL, which are both kind of like imaging techniques that are sensitive to blood flow, so they'll fit nicely together. But I imagine once we get through that, we'll have like an hour of extra time. So if anyone has any topics that they would like to hear about, for example, if you want to know more about MRI imaging artifacts or maybe image processing methods that could be applicable to the class, feel free to let me know. Maybe in the survey form I send it at the end of the class or something like that. I will be happy to kind of take suggestions or kind of fill space on my own, or just let everyone go early, who knows. Okay, so first I want to kind of start with a refresher on what we were talking about last time, T2 weighted imaging. And hopefully this looks a little bit familiar. I've got a pulse sequence diagram that we're gonna go through here. I figured this would be a good reminder. So let's get into it. When we're talking about a T2 weighted imaging sequence, we're going to draw one out here and I'll kind of show you what it looks like, and then we'll dig a little bit more into why it looks the way it does. T2 weighted imaging sequences typically use, I'm going to make this marker a little bit smaller. They use gradient echo methods. So it's a gradient echo sequence, usually. That can be abbreviated as either GE or GRE. The R stands for recalled. So it could be like gradient echo or gradient recalled echo. Worth noting that this GE is a separate acronym from General Electric, who makes MRI scanners. So the first thing that we do in this kind of sequence is we have our 90-degree RF pulse. And all my markers are very thick. And hopefully you guys remember, when we're doing this RF pulse, we want to only affect one slice of tissue, generally a millimeter or a couple millimeters thick. So we're going to apply the slice selection gradient at the same time as our radiofrequency pulse in order to interact with spins or tip the NMV in one slice of tissue specifically. So I'm going to draw that as a positive gradient and also thin this marker while I'm thinking about it. So that's kind of representing that we're targeting a specific slice. In theory, like the size of this box could tell us the amplitude of our slice selection gradient, although it's a little bit arbitrary in this diagram, which is fine by me. Another thing that's important is that we balance our gradients to make sure we don't induce any phase differences in any direction other than the phase encoding direction. So I'm going to add a negative lobe onto the slice selection gradient. And as I kind of mentioned last time, so long as the area under these two squares is equivalent, the phase differences that they incur will balance out. So it doesn't need to be as long as the first one, so long as it's a stronger gradient. It just kind of saves me some space in the pulse sequence diagram. Now that we've got our NMV in the transverse plane, we can record it. But in order to make sense of that signal, we want to spatially encode information in our phase direction, our Y direction from back to front of the brain or the body typically, and our frequency encoding direction, which is kind of across the body from left to right. So maybe this will ring a bell. We are allowed to encode our phase information whenever we want because it stays once we put it there. It doesn't rely on the presence of a gradient, unlike changes in precessional frequency in our frequency encoding direction. So we've got this phase encoding symbol here. It's generally drawn as kind of a circle with multiple lines, kind of looks maybe like an armadillo shell, if that helps at all. I'm just kind of keeping it to 3 lines up and 3 lines down here. But this represents that we're going to be using different phase encoding gradients of different magnitudes when we repeat this pulse sequence to acquire multiple lines of k-space, which we'll touch on again in a second. And then at the same time as we do that, we can have our negative lobe of our frequency encoding gradient, because we need to balance out the phase that the positive lobe of the frequency encoding gradient will incur as it is on. And this should be about the same width, negative to positive, so that our phase differences are balanced at the middle of our readout, which I will draw here. There's red as our echo. Not the worst one I've ever drawn. Yeah, so the signal line is showing when we're actually recording signal. We could record signal anytime after we do the 90-degree pulse, but we're actually only recording it during that frequency encoding window where the signal actually means something that we can understand, because we have that balanced phase difference. Sorry, we have balanced out our kind of like dephasing effects and then rephasing and then dephasing again in the echo, and that's just kind of due to how we've laid out our gradients to account for the fact that when the frequency encoding gradient is on and we're reading out signal, we are also causing dephasing just because some spins are spinning faster than others. I also wanted to remind us about how this looks in k-space, which I talked about a little bit. That's what the square is on the right side of the screen. It's just a general k-space layout, I guess. So this direction is our positive ky direction, and this direction is our positive kx direction. That's an x. So generally the trajectory we follow, remember the gradients that we use can kind of tell us where we are in k-space, and if we record signal or if we record data at any given time, we can we can know where that data goes in k-space based upon which gradients we've applied so far. Kind of funny, but very useful. So after the 90-degree pulse, we start in the center of k-space. And then when we have our phase encoding gradient and our negative frequency encoding gradient, those are going to move us. Well, it depends on the phase encoding gradient. So let me highlight one. We're going to say it is the largest positive lobe. I'm just going to make that even thicker so that you kind of see what I'm talking about. So that ball that I've drawn is being replaced by one positive phase encoding gradient. So in this iteration, or in this step of our acquisition process, we are moving both up in the y direction. That's what our phase encoding gradient does to our pointed k-space. And then the frequency encoding gradient, we're going to be moving to the left in the negative kx direction. And we can do those at the same time. So our movement at the point of these two gradients being on, the phase encoding and the negative frequency encoding, is going to move our point in a diagonal line to the corner of our k-space at the top left. Phase encoding up, frequency encoding left. And then all that's left is to account for the positive frequency encoding gradient, which is going to move us all the way across k-space from the left to right. I'm drawing that in red because that's when we're actually reading signal and we're recording that echo, and then that echo slots into that line of k-space. Remember, hopefully, that k-space is filled with various echoes that we collect from our body of interest. And once we've collected enough of them, we can use that inverse Fourier transform to take all of this information that's in frequency space and turn it into a spatial image of the brain or something else. Now, I don't know if you've checked in your time working with MRI images, but typically a resolution of MRI images is somewhere between like 64 by 64 pixels for a given slice, or 128 by 128, or 256 by 256. That I would say is probably the most common, 256. But what that means is that we need the same number of rows and columns in our k-space to produce an image of that size. So this one echo that we've collected is 1 out of 256, and we're going to have to repeat the same thing 255 more times to fill the other, lines of k-space with other echoes, right? So you end up having to collect a lot of data. And we're going to be using the same sequence the whole time. The only thing that's going to change is our vertical location of the echo we're recording in k-space, which is determined by the amplitude and direction of our phase encoding gradient. So hopefully that all makes sense. Sounds like collecting 256 echoes would take a long time, and it kind of does. A T2 weighted image would probably be between, like, I don't know, 2 to 5 or maybe even 6 minutes, depending on your scanner. I can't really recall how long ours is on the Children's Hospital scanner. I think it's around 5 minutes. So it does take a while, just because we need to kind of let our signal regrow before we tip it again and all that stuff. But one thing that's worth noting about this gradient echo sequence that I've just drawn is that nothing that I've drawn here is determining the T2 weighting of our image. This gradient echo sequence isn't inherently a T2 sequence. The thing that determines the weighting of our image is the TR and the TE, which I talked about a little bit last time, kind of outlined. I will draw them again here, but first I need to have another 90-degree pulse in this direction. So the TR, the repetition time of our image, is the time between the start of one version or one step of the pulse sequence and the beginning of the next echo acquisition step, if that makes sense. So we're going to be repeating this sequence 256 times. Every time there is the beginning of this gradient execution maneuver, that is the duration between those times is the TR. It's essentially kind of how long we let our signal rest or relax after a 90-degree pulse or some other flip or tip into the transverse plane, how much time we let our signal relax before we do that again. And then the TE, I'm just going to draw a wobbly line downwards, is the time between our tip into the transverse plane of the NMV and recording of the center of our echo. You can kind of choose how long you're going to signal or sample the echo for. So the echo could be kind of longer or shorter. You can choose how often you're going to sample it as well. That's called the readout bandwidth. Is it? Yeah, I think that's how often you sample the echo. But those details are kind of more detail about the echo and sampling it than we need to get into for this course. We're just going to kind of focus on the timing that you reach the kind of the center of that echo in your signal readout. Now, another way to quantify echo time, and this is also quite important, is the TE can also be described as the time at which you acquire the center point of k-space. Just kind of let that sink in and conveniently drink some coffee in the meantime. So yeah, sometimes when people talk about TE, they're talking about it for a whole slice acquisition of k-space, or perhaps even a whole volume acquisition. I'm only going to talk about two-dimensional k-space in these sessions, really, but it's possible and quite common actually on MRI scanners to acquire a three-dimensional k-space and then reconstruct the whole volume at once. So in the case of the brain, you would be doing something and then recording information in the X, Y, and KZ direction. And when you did the inverse Fourier transform, you wouldn't get a slice of the brain, you would get the whole volume of the image you're acquiring, which in this case would be the brain. That is faster, and it requires some fancy tricks and techniques to get a nice quality image of a 3D k-space, but it's possible. And later on in this session, we're going to be talking about techniques where you're acquiring the whole k-space at once, kind of as fast as possible, instead of one line at a time. This is just kind of a simpler example. In those cases where you're kind of acquiring more than one line of k-space at a time, it gets a little bit more abstract, but the TE there is determined by when you are acquiring the center point of k-space. It's essentially the same concept that we're talking about here, but much more practical. Like I talked about before, k-space is defined by having the general contrast of the image, the bright fuzzy whites and the dark fuzzy darks in the center of the image. That's where your general contrast is. And then on the outsides, there's all the fine details that don't define as much of the image, but are still very important, so we can actually have high resolution and distinguish between structures and all those kinds of things. So when we acquire the center point of K-space, we're acquiring kind of like the maximum, like the very general contrast in our image, and kind of just like the most general, the most general contrast possible. So when we're acquiring the center point, we're kind of pulling in like the maximum amount of information about our image at once, even though it may not be the most fine and well-defined information. It's kind of like the general bulk image that we're getting. So TE can also be the time that you acquire the center point of K-space. Hopefully that helps. It's very important for both the T1 imaging technique we're going to be talking about and diffusion tensor imaging or diffusion weight imaging, which we'll talk about later as well. But for now, I want to go back to talking about T2 weighting. So I have a very big question for the group. In this diagram where we've got two T2 curves from different samples, maybe white matter and gray matter, or fat and non-fatty tissue. When of these 3 time points that I have given on this graph, when would you choose to record the signal? If you want to participate in this little survey, you just can go to menti.com on your computer or your phone and type in that code 2505999, and then just give an answer, and we'll talk about the differences between these points, what I'm actually getting at here. I'll give like 30 seconds or so, and then we'll come back to chatting. I'm going to pull this up on my tablet. Oh no, the page isn't even open anymore. All right, we're apparently already on the results page, which is fine by me. Yeah, so question, when of the time points 1, 2, or 3 would you record signal? You guys are killing it. Clearly a sign that I can go faster. Sorry if I'm boring anyone. But yeah, that's completely right. In these 3 options that I gave you, we will want to record at time point 2. Let me jump back into OneNote so that we can briefly talk about why. I'm pretty sure this is, based on those results, something that everyone already understands, which is awesome, or at least has an intuitive sense of, which is perfect. Yeah, so the reason that we would measure our signal at time point 2, if we could, instead of the other 2, is because there is a fair difference in the red and the purple samples of tissue at this point, which means if we record signal at this point, the red tissue, or like the area where the red signal is coming from, is going to be darker than the area where the purple signal is coming from, right? And that gives us image contrast, which is what we want in MRI. Just to kind of like briefly mention, if we image at time point 1, both areas, red and purple, would be brighter, right? Because this is representing the amount of in-phase magnetization that's present in the transverse plane. And in this case, both of those lines are much higher, of course, because we're earlier on in the sequence. So this could be good as well, although those are just some poorly drawn arrows. But the idea of time point 1 is that the lines are kind of closer together, meaning that there's not going to be as much difference between our red and purple samples. which means it's going to be kind of harder to distinguish, and we're going to have a brighter brain, but it's not going to be able to tell us as much. So generally, we want to orient our sequences with our TRs and TEs to capture image contrast based upon a property that we're interested in. In this case, so far, we've been talking about T2. So we want a image to be timed correctly such that areas that have very quick T2 and their signal dephases quickly, those areas will be dark, whereas areas with longer T2s where signal stays in phase for longer, they'll remain bright. So kind of the rule of thumb for TR and TE, for a T2 weighted sequence, why did the people who created MRI make everything a T acronym? Who knows? But for TR, we want it to be long. And we want our TE to be long as well. Long, of course, is relative, but it kind of, just remembering long TR and long TE for T2 weighted imaging helps me at least kind of remember, why we would be doing those things, as opposed to the opposite of a short TR and short TE, which will give us something else. So the purpose of a long TR is we want our signal to fully regrow, right? And that's by that T1 longitudinal relaxation mechanism. We don't want there to be any differences between tissues in terms of how much signal has recovered in those areas. Otherwise, we'll be getting something that's kind of T1 weighted, where we see dark and bright areas depending on how quickly signal recovers in an area. So we want our TR to be long so that all signals have kind of fully recovered to their maximum, that 100% of the NMB magnitude, and then any differences we see should be because of T2 dephasing effects. And that's why we want our TE to be long. We want that to be long because we want to allow time. Let me just actually start at allow. We want to allow time for dephasing to occur. Right, if we have a very short TE, like we would if we recorded at time point 1, we wouldn't get as much contrast in T2 between tissues as if we waited a little bit longer and let some signal disperse and other signal kind of be retained. So long TR and long TE. Now I'll kind of remind that T2 times for tissues are somewhere between like 10 to 100 or 200 milliseconds. 200 is very slow, but I'd say like ballpark 50 milliseconds or so. So a long TE might be 30 to 50 milliseconds, which isn't that long at all. But it does kind of describe that we want to wait for T2 dephasing to occur. So here I've got an image of a T2 weighted image of the brain. This, I'll zoom in a little bit once this is finished. I don't think I'm going to write too many notes. I have a bunch of notes on this, but it's a lot of writing. So I'm just going to talk about the image and I'll fill it in when I give you guys the notes. This is a very nice resolution picture of the brain, right? Better than usual. It's because it's from a 7T scanner. And like I talked about before, the higher our field strength, the higher our resolution can be because there's a larger NMB and more signal to work with, which is great. So we have very high resolution, and we can see that areas where there is water, those areas are bright. That is because water has a long T2. The signal in there kind of stays in phase. It's fairly in fairly similar magnetic conditions. There's not any accelerated dephasing that we might see in fatty tissues, like the kind of darker areas on the screen, the white matter tracts. They've kind of lost their signal quite quickly, so they are darker in this image. So now we know that T2 weighted images use gradient echo sequences. And we know that by varying their TR and their TE, that's what determines whether this image is going to be T2 weighted or something else altogether. The reason that we use gradient echo sequences for T2, hello, thank you. They are fast. So we typically use gradient echo sequences for T2 because they're fast, because our T2 times, as I mentioned, are quite quick. 50 milliseconds isn't a lot of time for us to dephase our signal, rephase it, record that echo before the signal is just kind of lost to the T2 dephasing effects, which we can't reverse, right? I guess little thing worth noting here is that a gradient echo sequence measures T2 star, right? That's a 2. Not T2. That is true. If we wanted to measure T2, our true T2 curve, we would need to use a spin echo sequence, which is not as fast, right? So at any point in a spin echo sequence, there'll be more signal available, but we have to wait more time because we want our signal to dephase an amount, flip it with that 180-degree pulse, and then let things have the exact same amount of time to rephase in our echo. So spin echo sequence generally take a little bit longer, and T2 star waiting, so long as we can record our image fast enough, should be fine. It gives us the same kind of contrast. But we generally see bright water on images like this, right? So the brain, it's kind of a little bit harder to tell the difference between gray matter and white matter in this image than it might be in a T1 weighted image, but we get really, really clear contrast for water, which means these are very clinically relevant scans. And I am not a clinician. My understanding is often doing sequences fast and getting your kind of contrast as quickly as possible can be very useful. So perhaps you don't want to wait 7 minutes for your full T1 image. You can afford to use T2 because all you're interested in is water content in the brain, which helps to diagnose or identify areas of stroke or edema or lesioning. Those kind of things are all, they show up quite well on T2 scans. So my understanding is they're very useful for clinical applications. They're also the basis of diffusion weighted imaging and fMRI as well. So fast scans, good contrast, bright water. So we're really able to identify where water is in the brain. That's kind of my brief summary of T2 weighted imaging. There's a lot more to it than that, but that's an intro for you. And then of course the areas where tissue is most fatty and complex, those are dark as opposed to the brightness of water. So with that, I think we're moving on. Oh yes, right. Next, we're going to talk about the signal to noise ratio, which I have not segued into yet, so allow me to do that. The reason that we want to collect this image quickly is because our T2 effects are going to cause our signal to disperse quite quickly, right? So the sooner we collect, the more signal there is remaining. This comes back to this diagram that I drew up here. If we image at time point 1, we'd have lots of signal, but not much contrast. If we image at time point 2, we have less signal, but more contrast, so it might be more useful. Then time point 3, I didn't even mention because there's no signal left in the red sample that I've drawn, and the purple is essentially 0 as well. So we would just get kind of like a black box. Not helpful at all. And we want as much signal as possible because we have to maximize our signal to noise ratio. So that's kind of what I'm going to talk about next. That segue was not as natural as I hoped it was, but it's fine. Signal to noise ratio is a very important concept that applies to anybody who wants to scan somebody in an MRI or understand what their images mean. So let's chat about it. The signal to noise ratio, the explanation is kind of in the name, but it's worth getting some kind of exposure to what that exactly means. There is signal, which is what we have been talking about so far, our NMV and its precession and our recording it from a point of reference, which gives us this kind of sinusoidal curve. I'd like that to be thicker. I'm going to give it to, no, it's better. All right, great. So we have the signal. That's the precession of the NMV. Now we also have noise, which I haven't talked about yet before. Noise is just intrinsic random error that's just intrinsic to the machine that we're using, right? So Noise can be defined as random or sometimes referred to as stochastic. Same thing, random error due to normal machine functioning. The machine I'm talking about in this case is the MRI, but of course noise is present for any digital recording method. And it looks, rather than being a smooth, predictable signal that we're interested in, it just looks like small variations determined basically by chance. Obviously, this is a human's interpretation of random, so it's not going to be perfect, but the idea is if this is one version of noise, the next time we do the exact same thing, the noise may be different. It's also quite small in amplitude, so not nearly as large as the signal that we record, but it does kind of get overlaid with our signal to give us a result that's just inherently less accurate than the signal itself. Right, I will stop there because I'm drawing off the screen. The idea, we can still see our signal here, but if we assume that the signal is true, that it is like the truth of what's happening in the tissue, we're going to be disappointed because those little variations in the signal amplitude are not due to any physical mechanism that we're interested in. They're just because some of the the conductance of our wiring and cables is imperfect, or the recording device that we're using to actually record the signal has some measurement errors, those kinds of things. I'm sure this isn't new to anybody. But the signal here we know is predictable. It's our, actual, the thing that we're interested in. And it's also consistent, right? Just by its nature, if it's predictable, we can understand how it's going to manifest given certain grading conditions or other magnetic manipulations, whereas noise is random, right? And it's typically small variations. Now, this affects our MRI images. I'm sure most people here, or possibly everyone, has had the experience of taking a picture at night where there is not much information to be collected from the world. It's dark out there, there's not much light, and that's when your images look grainy. The same thing happens in MRI. Essentially, if the image that we're collecting, the signal is too low, or there's not much information to be collected, that kind of random variation in everything about the MRI machine takes over and makes the MRI image look grainy generally. So I've got a handy animation here which does something. In this version of the Amios page, they have the same signal here, the same brain, but they vary the amount of noise. And I guess we can kind of just visualize the result here. So you can see as we're progressing, the noise is decreasing and the resulting image is clearer, right? It'll play again here. But as there's more noise, we can see the result on the right looks grainier, looks blurrier, and that's very important, right? Because if we're looking at which areas are dark or light and inferring where white matter is or gray matter is or something like that, the fact that there are areas that should be dark that are lighter than they're supposed to be just due to noise is very important, as you might imagine. Now, the reality is we actually can't change the amount of noise in our data as much as this website would like us to believe, because it's inherent to the scanner that we're using. And I don't know about you, but I can't buy a new scanner every year, and neither can the hospital that I work at. They're very expensive and time consuming to install and that kind of stuff. So the level of noise that we have to deal with in our data is usually quite static. It's always the same. So what we need to do instead to change our signal to noise ratio is increase the amount of signal that we are recording, right? So I've answered my own question. How can we account for noise? The answer is collect more signal. To kind of outweigh the effects of noise. Obviously, it's not that simple, as there are many imaging sequences that I used in my PhD that are still quite noisy, and that's fine. It's just kind of the state of the technology that could be improved by varying parameters in the scan sequence, like TR and TE. And here's where our poll comes in. So just kind of a quick preface. I did this on Zoom, as I've learned that Menti, you're allowed to have 2 questions maximum, and I want to give 8 or so. Questions is kind of saying, if we assume the scan is the same, what'll happen to our SNR if we change one parameter? This is something that Brad Goodyear did in his class, and it was kind of a moment for me when a lot of the knowledge I'd been gaining about MRI kind of came together. So it might take a little bit of thinking to work through this stuff, but hopefully it's as useful for you as it was for me. I'm going to put up a poll in Zoom. Hopefully you can see it. I can see it on my computer, so that's good. Yeah, just take a minute. I'll give like a minute or two. We'll see how many people respond here. Just thinking about what will happen if we vary a given parameter. Will that increase our SNR or decrease it? And then we'll kind of talk about why each parameter would have the effect that it has. So yeah, take your time. I see there's a timer on the poll. Let's say 5 minutes or so. Maybe I'll cut that short if people breeze through it. Ready? Resumed our recording. Hopefully that didn't feel too much like a quiz, a unjustified quiz to you. Hopefully it's useful, but let's talk about our answers here. So I'll just gonna go one question at a time. Happy to answer any questions, of course, that come up with this. And I realize that some of the parameters might have been kind of less clear than others, but that's okay. By explaining them, we'll kind of get a better idea of what it was that I meant in the first place. Okay, so first, what happens to our SNR if all other things are equal if we increase our voxel size? Correct answer there is our SNR will increase rather than decrease, which most of you got, so well done there. So I gotta have my poll at the bottom. Okay, so yeah, question 1, SNR increases. And the reason for that is that noise is always the same, right? It affects each voxel at the same, with the same like a magnitude, the same amount of effect of noise on each voxel, regardless of their size. If there's a voxel that's 10 millimeters wide versus 1 millimeter wide, they both have an equally likely random chance of machine error that will cause that area to be, slightly lighter, or slightly darker than it's supposed to be. But the voxel size determines how many spins are in a given location that are actually contributing meaningful information to the brightness of that pixel or that voxel, right? So if we start with a voxel that captures these 4 spins, then our signal from this area, I guess I'll just keep it blue, would maybe look, something like this, some variation of a given magnitude, which is great. But if we consider what happens when we create a voxel that encompasses 9 spins instead, that's more than double the 4 we were recording from previously, right? So the amount of actual meaningful signal that we collect would more than double in proportion. So perhaps the new sine wave would look something like this. What this means is essentially we're casting a wider net to collect information in a region, and because we are collecting more signal, the SNR is going to increase because noise is static, it's the same, whereas our signal that we're recording has increased for that given voxel. So we're going to have lower resolution, true, because our voxels have increased in size, which means maybe in a broad example, we go from 128 by 128 down to 64 by 64. So our image itself will be blurrier, but the SNR will be higher. Okay, question 2 was what happens if we use spin echo instead of gradient echo? Again, the answer is our SNR would increase. Just kind of browse away over here. So this comes back to our T2 star versus T2 decay curves. So spin echo instead of gradient echo. And I don't think I'll need to draw all these out, but this image came to mind, so I'm just going to quickly draw it. So if we consider our T2 star curve, which I'm drawing in green here, and our T2 curve, which I've drawn in orange, gradient echo generally is sensitive to T2 star effects, right? So if all parameters of our sequence are the same, except we've switched from spin echo to gradient echo, we are now measuring signal along the T2 curve because we've canceled out all those imperfections in the magnetic field and gradients and conductive materials that are causing increased dephasing in T2 star. And we're just looking at T2 effects, which means that there's kind of more signal available for our echo. So generally, if we use spin echo, we have a higher SNR than gradient echo just because we're on that T2 curve now instead of T2 star. Of course, I did already mention that spin echo takes longer than gradient echo. So this is a bit of a contrived example, but that's kind of the answer to that one anyway. If we manage to keep the sequence exactly the same, then spin echo would have a higher SNR than gradient echo generally. I've got a question here, so let me pause to read that. Can you explain why noise is static no matter voxel size? For example, if there's noise because of imperfections in the B0 field, then there are more imperfections in the larger voxel, right? Yeah, okay, sorry, there's just a follow-up there as well. So I guess I would say like imperfections in our B0 field are not part of noise. That's kind of a part, that's an imperfection that would affect something like T2 star and inaccuracies in the signal that we measure compared to what we expect. But noise is, instead of something that's constant like that, like an imperfection in the B0 field might mean that there's an area where the field is always weaker than it should be. That's a constant influence on the data that could be counteracted by using spin echo instead of gradient echo or something like that. Noise is just random stochastic errors that are just because we're using a digital machine that cannot be designed perfectly, it cannot function perfectly. Even just the idea of fluctuations in power supply to our coils or something like that are going to cause random errors and random variations that are going to influence our resultant image. So you're right that having a larger voxel would kind of mean that it's like an imperfection in the magnetic field, for example, would affect more tissue in that voxel and might kind of draw the gray scale or the lightness of that pixel further away from biological accuracy, but that's not noise. That's a different kind of artifact that we're not considering in the signal to noise ratio. We're just considering random errors due to machine imperfections at this point, which looks more like random ups and downs. And you mentioned in your follow-up kind of that pluses and minuses of noise can cancel each other out. That's exactly right. And that's why sometimes we average images, which is the last of these poll questions. So hopefully that helps a little bit. Increasing voxel size generally increases our SNR because the random effects of noise are balanced out a little more by increased signal. If I didn't quite get there, please post a follow-up. I'll be happy to answer more. Okay, so question 3 in this poll was, what happens to SNR if we increase our TR, our time between repetitions of our pulse sequence? SNR increases in that scenario, so well done, everyone. Increasing our TR allows tissue to have more time for the NMV to recover, right? So if our TR is too short, some areas where T1 is quite long will have a net magnetization vector that hasn't fully recovered, and therefore when we tip that NMV, it's going to contribute less signal in the transverse plane for us to measure. So increasing our TR kind of guarantees there's more time for signal to regrow, and in our subsequent pulses, we will have more access to more signal. Excuse me. Also worth noting that T1 effects are described by an exponential growth, right? So it's very quick at the start and then much slower and more gradual later on as they kind of approach that 100% magnitude asymptote. So even when the NMV has really largely recovered, allowing more time will still allow the NMV to have more time to actually recover, even a little bit. So generally increasing our TR increases our SNR. I've got another question here. Oh, so the noise in MRI is white additive Gaussian. What is the origin of being white or Gaussian, or both from the device? I will be honest, I do not know what you're talking about. Maybe not the best thing to admit, but yeah, I would need to look that up in order to give you a meaningful answer, and I can definitely do that. But at the moment, I can't give you a solid answer there. Aside from just describing noise as kind of like random variations due to machine error, that's kind of the level that I want to stick at. And I'm happy to dig into more detail, but I will need to do that on my own time to understand the question. That may be due to my psychology background rather than solid engineering. My math education in university stopped at second year. But let's move on from my lacking calculus knowledge. So what happens if we decrease our field strength in MRI? The correct answer here, which most people got, is SNR will decrease. So well done. This is because of the fact that our NMB magnitude are imbalanced between spins oriented in the up or the parallel orientation versus anti-parallel orientation. That is determined by field strength. So at higher field strengths, the NMV is larger. I kind of alluded to that when I was talking about 70 images with that T2 weighted image up above. If we decrease our field strength, we go in the other direction where there are less parallel oriented spins, disproportionately compared to anti-parallel orientation. So there's actually just less signal available for us to record, which means our SNR decreases because noise is always the same, but now we have less signal. So signal to noise ratio goes down. Question 5 was, what happens if we increase our echo time? This one was fairly split. The answer is generally our signal to noise ratio will decrease if we increase our echo time. This is because if we just go back to this drawing that I've conveniently got here, the longer that we wait to record signal, the more time that we are giving our NMB to dephase, right? Whether that's on the T2 star curve or the T2 curve, the longer that we wait, the more signal will have irreversibly dephased. And what that means is that in the transverse plane, when we record our signal, the magnitude of that signal is smaller. So if we increase our echo time, we're waiting longer to record our signal, which means T2 effects have a longer time to set in. Okay, final 3 questions. What happens if we increase our slice thickness? In that case, signal to noise ratio will increase. This is for the same reason as our voxel size question at the very start. We are now recording signal from more spins, right? And we're essentially just increasing the size of each individual voxel by modifying the height of that voxel, the Z height, the slice thickness. So we're recording information from more spins, which means we're recording more actual signal, which can kind of outweigh the noise. So SNR increases when we increase slice thickness. That's why when you're doing something like fMRI or DTI, you see kind of higher slice thicknesses than you might in structural imaging, because there's less signal available in those sequences. So you need to kind of have thicker slices in order to actually just collect enough signal to not be looking at a noisy image. Okay, second last question. What happens if we decrease our flip angle? The answer here, which most people got, is SNR decreases. So well done again. So far, we've been talking about 90-degree pulses pretty much exclusively. That'll change in a little bit. But the reason that SNR decreases when we decrease our flip angle is because we can only measure signal in the transverse plane, right? So when we tip our NMV, we are measuring the transverse component of the NMV. So if we don't tip it all the way, if we tip it 45 degrees instead of 90, the transverse component of the NMV will be lower, just kind of by definition. Just to kind of get across what I'm meaning here, in case anyone's not following. If we have an NMV that is vertical and then we tip it 45 degrees, or we tip it 90 degrees, in both cases, we are measuring this component of it, right? So in the 90-degree example, that component is maximized because the whole vector has been tipped orthogonally. Whereas in the other example here with a 45-ish degree pulse, I realize that's not 45 degrees, that the magnitude of the transverse component is lower. So decrease flip angle, decrease SNR. There are advantages, though, to why we would not use a 90-degree pulse. In fact, pretty much no one uses 90-degree pulses. So there's a reason that we can kind of account for that. And finally, what happens if we record our image twice and average the results? SNR increases when we average our images. And this comes back to the kind of diagram I've got drawn here, where because we're using the physical mechanisms of MRI to generate the signal that I've got drawn in blue here, it's going to be the same each time that we record that same signal. Because we've got an NMV, we're manipulating it with magnetism, and we're letting it dephase and rephase and all that fun stuff. The signal will act the exact same every time in a perfect world. Our world is semi-perfect, so it may not be exactly the same, but it's closer to consistent than noises, which is completely random. It's just intrinsic to the machine. And if we run the same experiment twice, because it's random, some voxels will have noise that kind of increases the intensity in that voxel one time and decreases it the other time. And then if we average those together, the signal stays the same. So our two signals will, and when averaged, produce the same result, whereas noise might sometimes cancel itself out. And this comes back to Catherine's question earlier. So if we average multiple copies of the same image, we will have a higher SNR because we've essentially collected more signal. And when we average them, noise will kind of cancel itself out, which actually produces quite a big increase to our SNR. All right, took a little bit of time to get through, but I'm glad we did it. Hopefully everybody learned something or rather from those questions. I will just kind of close that. Don't think you guys could see the results, but generally we were at like 75-ish% correct on every question, except for the TE one, which was split 50-50. Got a question here, and then after I get to this question, we'll just take a break. Even without fMRI, we're behind where I thought we would be, so we'll see how much we get through in the second half of the session. But yeah, okay, so Chelsea has a question asking if higher resolution images would have more noise and sort of be lower quality. Yeah, that's true, definitely true. Generally, a image with more voxels, noise has a higher chance of impacting the image, because each voxel or pixel itself has less signal that's been kind of like binned into it. If we think of imaging a part of the body, there's a consistent amount of signal available, and if we divide that into smaller and smaller bins, then noise will kind of outweigh the available signal in each bin. So the reason that we're able to take an image as nice as this one of the brain is because we've increased our SNR in other ways. In this case, we're using a 7T scanner instead of a 3T or a 1.5T. But yeah, generally when we increase our resolution, which allows us to actually look at finer details between structures, like for example, here you can see some subcortical structures between like these dark white matter tracks, which might be harder to image on a smaller or a lower quality scanner. When we have higher resolution, we are able to actually see those differences. They don't just get blurred into the same level of gray, but we have more noise to, each voxel or pixel is more influenced by noise individually. So that comes back to kind of our voxel size and resolution. It's a trade-off, but yeah, you've got it exactly right there. All right, so we are at 11:06. I will say let's have a break until 11:15. Go grab some coffee or do whatever it is you do on these breaks. And we will come back and talk about T1 imaging and maybe a bit of DTI. All right, so coming back, recording is started again. I just wanted to address the question of noise and MRI being defined by a white additive Gaussian. Over the break, I looked it up and have a better idea of what exactly that means. So for those unaware, like myself previously, this is a model of noise. The Gaussian distribution is the normal distribution, which I think is on this page somewhere. Yeah, something like this, which essentially just means that, across a sample, there's a mean, generally 0, and then it's, the likelihood of something above or below that mean is equal. And that indeed describes noise and MRI quite well. So there's 3 terms kind of in that model of noise that we're talking about: white, additive, and Gaussian. So the first one, Gaussian, means that the noise in the image has equal likelihood of either increasing intensity in a voxel or decreasing it, which I had this picture up earlier. So kind of just seeing, if we look at this image of just like static you might see on your TV or back in the day or whatever else, there's kind of an equal likelihood that any voxel in this image is going to be white or dark when we're considering MRI. In this case, I guess every voxel was black, and then the noise would have been added on top to make them lighter. But anyway, in MRI, it has an equal chance of either increasing or decreasing the intensity of signal in a voxel. The reason that it's white additive Gaussian is this is interestingly an analogy to white light, which has an equal amount of light or photons at any given frequency. So what this means in the case of noise is that this noise is present regardless of the frequency that you're sampling the MRI sequence. Like I mentioned before, you can sample your echo or your MRI image at various frequencies, and that, I guess, is a little bit outside the scope of this tutorial series, but it is a parameter you can change, what frequency you're sampling your signal at. It's also quite an important one, and the white part of this Gaussian model of noise means that regardless of the frequency that you're sampling your signal, oh boy, you're still going to see the same noise, the same effect of that noise. And then additive just means it's kind of added on top of any other noise or actual signal in your sample. So it just gets kind of overlaid, and it's always there. So yeah, that's kind of a more technical way of describing what noise looks like in MRI. Previously, I was just saying it's random and constant. This is the same kind of thing. So thanks for that, Zara. I learned something. I would like to go back to OneNote. All right, cool. So let's dive into, now that we know a little bit about SNR, T1 weighted imaging. Hooray. Okay, so we just, before the break, we're talking about SNR, and before that we were talking about how you weight an image by T2 with that little Menti quiz. The same kind of ideas apply to T1 weighted imaging, we want to modify our TR and TE to find contrast based upon differences in recovery or longitudinal regrowth of signal in tissues, which is what T1 defines, right? So in this little graph that I've drawn, we again would be imaging around time point 2 because there is a difference in the amount of signal available between our purple sample of tissue and our red sample of tissue. And as a reminder, generally, fatty tissues have shorter T1 times because they're more easily able to exchange the energy that they absorb from the RF pulse. They exchange it into other populations of tissue and just give it away. Whereas water or non-fatty tissue has a harder time of doing that. So the signal kind of stays around for longer. It takes longer to regrow. So wrapping up that point before I jump into something else. The rule of thumb for T1 weighted imaging is we want our TR to be short. Interesting. Let's dig into that in a second or two. Actually, no, let's dig into it now. So the reason that we want TR to be short is because instead of like T2 imaging, we do not want to give our NMV time to recover equally in all samples, right? We want to have a shorter TR so that some samples have a high amount of signal. They have got that quick regrowth going on, whereas other samples have not regrown as much. And that's why our purple arrow here is shorter than the red arrow, because we haven't given enough time for both of them to catch up like they would over here if we waited longer. So a shorter TR generally between pulses, and we want our TE to be short as well. And the reason for this, let me actually just fill out the TR part. Don't give time for full NMV recovery. Hopefully that summarizes that pretty well. I'll just move down a little bit. Okay, so now we want our TE to be short. And the reason for this is we want to remove or just kind of exclude any T2 dephasing effects. Right, so we're all familiar with the T2 decay curve now. If we wait any amount of time, the signal in the transverse plane is going to dephase. That is a T2 mechanism. It is not dependent upon T1. And if we want a T1 weighted image, we want to minimize the effect of T2 on our image. So we want a short TE to acquire signal as quickly as we can before any dephasing has occurred. And that will kind of increase our T1 weighting, kind of just the contrast in the image that's dependent upon only regrowth of the NMV in tissue rather than dephasing. Okay, so there's a problem here. And this is why I talk about T1 weighted imaging after T2 weighted imaging, is it's a little bit more complicated. What we have at time point 2 in this image is a difference in the NMV, which is good, but it's in the Z direction, right? There's a different amount of magnetization that has regrown to realign with the B0 field in the conventional Z direction in MRI. So in order to measure this, we need to tip this newly regrown MZ magnetization into the transverse plane. And that requires us to have another 90-degree pulse or another RF pulse to tip this vector that we're interested in into the transverse plane. So I have some animations which will help to kind of solidify this, hopefully. All right, so we've got two tissue types here. There's the bright red and the dark red. And bright red has a shorter T1, which means it regrows more quickly than the dark red. So here, this animation is going to show kind of how we measure signal from each. Oh, I got it backwards. My apologies. So dark red is recovering faster than bright red. So first, there's a 90-degree pulse, and then we allow some time for recovery to happen, and then there's a second 90-degree pulse. And then we just kind of pause after the end of those two pulses. So right around there. So this is when we're actually recording signal. We've pulsed once, we've let things regrow, and we've done another 90-degree pulse, and now we're recording signal. And you can see how in the dark red sample, the arrow is longer than the bright red sample, right? That's because when we did that 90-degree pulse, the Z-aligned component of the NMV got tipped, and it was larger for the dark red sample than the bright red. And now we're going to see a difference in the tissues of our reconstructed image, thanks to our frequency and phase encoding. So I'll play this once again, just to kind of give you an idea of the trajectory of the T1 weighted pulse sequence. There are 2 RF pulses, and hopefully this helps you to understand why. Got another one here. Yeah, okay. This animation I've never made sense of, and I'm okay with that. But the first half of it I think is useful, which is just kind of getting at the idea that we want a shorter TR, because if we wait long enough, then those 2 samples we were just showing both recover to the same amount, right? What confuses me is this next part, where they've kind of switched from showing MZ magnetization to transverse magnetization. But we're kind of getting at why you'd want a short TR and a short TE in this animation. You want it short enough that there's that difference between MZ components of the NMB, and you want your short TE so that there's no time for dephasing effects to occur. And yeah, I would kind of take that away from this animation rather than kind of trying to understand the trajectory of their lines here, because they kind of switch it on you about halfway through. But hopefully that explains a little bit, or helps to kind of visualize why you would want a short TE and a short TR for a T1 weighted sequence. Now it's worth mentioning here, if you look at a T1 weighted sequence and a T2 weighted sequence, the TE for the T1 weighted sequence will be longer than the T2 weighted sequence. That's because TE, again, is measured as the time from the first 90-degree pulse to the time that you acquire the center of your echo, or the center of K-space. And that's going to be longer because you need to give time between that first 90-degree pulse and the second 90-degree pulse for longitudinal regrowth to occur. So the long TR, long TE for T2, and short TE, short TR for T1, they don't exactly overlap neatly, but it does kind of help to cement a couple concepts in there in terms of when you would actually be recording signal and why. So generally T1 sequences take longer than T2 because you need to allow time for longitudinal regrowth. So let's draw a T1 weighted sequence. I'm just going to kind of speed through this, as we've already done it once and have some other stuff to touch on, which is cool. So we've got a 90-degree pulse. Then we wait some amount of time and to allow for longitudinal regrowth. And then we've got another 90-degree pulse where we're now interested in that regrown component of the NMB. In both cases, we need to have our typical slice selection gradient. And then after we've done the second 90-degree pulse, we want to acquire data as quick as possible, right? So soon after that second 90-degree pulse, we're going to start phase encoding our data and frequency encoding it. Let's see, I'll turn this to a dark blue rather than a lighter blue. And for just kind of simplification purposes, I'm going to draw another gradient echo sequence where we have negative lobes of gradients, which I've already started doing. And then we record our echo here, right? And so we need these two 90-degree pulses, and then we have our chosen TR and TE above to weight this image sequence by T1, right? We could also do a spin echo sequence where we add like a 180-degree pulse over here, and then we change something like our frequency encoding gradient to a positive lobe and another positive lobe and record later. But essentially, I drew gradient because it's less to fit on one page. If anyone needs an example, written down in the notes of a spin echo sequence, there's one in the previous set of notes that I sent out. So now we've added even more time to our imaging sequence, right? We've got to wait for two pulses to occur. We have to, after that second pulse, wait enough time for the NMB to then kind of fully recover between tissues in order to make sure that our next set of two pulses generates the same kind of contrast. Essentially, this is going to take forever if we're recording 100 or 200 lines of K-space. It's going to take so much longer because we've essentially doubled the amount of time we have to wait for our signal to be prepared in order for us to actually image it. So I'm going to tell you now about a couple techniques used in modern T1 imaging on a GE scanner or a Siemens scanner. And that might be the last thing we kind of touch on today. But they are cool and worth kind of knowing about to understand why don't MRI sequences take literally forever these days. So the first is this thing called steady state imaging. This is a fairly universal concept in order to speed up scan times. Let's see if I can fit everything on one slide. The idea here is, actually, I kind of want that space. I'll just go back. Okay, so consider this this example, and it'll all come together. Let's do a flip angle that is less than 90 degrees, because that immediately speeds up our scan, right? It lowers our SNR like we've talked about, but it does speed up our scan. So we're going to do a 30-degree flip angle. Oh, that is much longer than it should be. Something like this, right? And then we give a little bit of time for our NMV to recover. So I'm going to let it recover about halfway here. Now there's say like 15 degrees between this and the z-axis. At this point, our z component is shorter than it originally was, right? Because the NMV hasn't fully regrown. Apologies for my disproportionate drawings here, but I'm sure they'll be good enough for you to get the idea. And we've got this transverse component as well. Now we are going to tip another 30 degrees. And for simplicity's sake, I'm going to consider just the z component of this vector that I've drawn, although of course there'd be some additive effects, but bear with me here. So now we've got this vertical portion that's tipped 30 degrees. It's relatively proportionate. And then we allow it to recover, right? Let's say it gets about halfway back. And then we've got this, this new longitudinal component that I'm going to draw in yellow, the most visible color. And then it's got a transverse component as well. And then we could tip that again and see the same kind of effect. And what I'm getting at here is if we don't wait long enough for the net magnetization vector to fully recover, each subsequent flip angle is going to give us kind of a smaller and smaller longitudinal component of the NMB, which means we're kind of imaging, or we have access to less signal every time, until suddenly things even out. So the way this actually looks in reality, and this is something that's done all the time, is if we consider our T1 regrowth chart that I've got up a couple times, instead of looking like, from 0 to 100 roughly, it's going to look something like this if we follow this paradigm of 30-degree pulses and short TRs. So instead of going all the way to 0, it's going to drop to say like, well, I don't know, 70% or something like that. 70 degrees. The actual number doesn't really matter. I'll just kind of give you a ballpark. So it's going to start at that point and recover a little bit like this. And then we're going to, before it has a chance to get back to 100, we're going to do another pulse, which drops it even further. And then it's going to recover and drop and recover. But then magically, at a certain point, the amount of signal that's tipped into the transverse plane and the amount of regrowth that happen become quite consistent. And this is when we would say the NMV has reached a steady state. So you can see how this kind of plateau that's reached is the same every time. It might not be at this exact quantity. It depends on a lot of factors, but the idea is that the amount of magnetization that you are now observing is the same instead of changing every time. And this allows you to measure information from the NMV in a consistent way without waiting forever for the NMV to recover fully, right? Because that previously we've been talking about letting the NMV recover fully because then we have a consistent magnitude to record. Now we can do that, have that consistent magnitude. It's going to be less than 100%, but it's still consistent, which means our echoes that we collect are all going to have the same magnitude. They're not going to be influenced by the having different amplitudes just based upon how long we've let our NMB recover. And then in the this applies to the transverse plane as well. So the graph there looks something like quick decay, and then suddenly the NMB is tipped into the transverse plane again. So there's kind of a jump in signal, And then decay again, and jump, decay. And again, these two curves are not proportionate with each other. I just want to kind of give you an idea of the general shape of this phenomenon. But T2 weighted image, or like transverse plane magnetization, can also reach a steady state. Hopefully this is making sense for everybody. If not, I'll keep an eye out for questions. This is very important because it allows us to speed up our scans quite a bit. We can now shorten our TR by quite a lot and still be able to predict the amount of magnetization that we're actually able to observe. So just to kind of summarize here, a steady state will be reached eventually, even if the NMV doesn't fully recover. Now, this is kind of, there's some new language to describe this. Generally, the pulses, I'm just going to kind of briefly highlight over here. Oh, that does not show up very well. Let me just circle it in green. These pulses would be known as preparation pulses, because you're not really going to record signal from the echoes or the transverse component of the magnetization vector if they're not kind of the same amplitude as everything else. You'd have to bring in some math to account for that, and it really differs depending on tissue types and field inhomogeneities, all those kinds of things. So these are now called preparation pulses, and then we're actually acquiring echoes from the NMV when it's at a steady state. The steady state can either be reached immediately, which would be very convenient, or it can take up to like 40 or 50 of these preparation pulses. So it can take quite a while. There might still be a payoff in time once you get there. So it could still be worthwhile. But I'll just put a note here, can take from 0 to 40 or 50 preparation pulses. But there's actually techniques that allow us to reach the steady state faster. I'm going to give myself a little bit of space here. The most kind of common one is a linearly increasing flip angle. So that can help us reach steady state faster. And I'm going over this because it is basically the basis of T1 imaging on the MRI scanner. So what I mean by linearly increasing is the flip angle, which is frequently described with an alpha symbol. For the first pulse might be like 3 degrees, very short, or a very, very small tip. And then next time you tip it, it'll be 6. And next time after that, it'll be 9. And it's not necessarily always the same. Let me just scroll down my notes to pull up the list of values from the text. Okay, so then after this, we'll go to 13 and then 16 and 20 and so on, and bigger jumps until we reach about 60 degrees. So it ends up being quite a significant flip angle. But this kind of process, depending on your tissue and your scanner and your gradients, all this kind of stuff, you can modify your flip angle to prepare tissue of interest quite quickly. So instead of like 50 pulses, you get there in 3 to 8, something like that. Generally, the ballpark for steady state imaging is around 8 TRs, if I remember correctly, from Brad's imaging class, Dr. Goodyear. But yeah, this is kind of, there are techniques that allow us to reach the steady state more quickly, which is very, very valuable and allows us to then image our, record our echoes at the same level of consistency, at the same magnitude, and all that fun stuff. So this is the first trick that it really, really helps to speed up T1 imaging. The second is this thing called the inversion pulse, which I haven't talked about yet, but is also very, very common. So let me go through this example as well. Yeah, I'll keep an eye out for questions in case that didn't fully sink in yet. So, no, I'm drawing on the wrong graph. although it'll be relevant eventually. In the case of an invergent pulse, instead of using a 90-degree flip angle or a 10-degree flip angle or something smaller than 90, we use a 180-degree flip angle, right? This may not be news to some of you, but maybe it is to others. And this causes our NMV to actually fully flip and be oriented anti-parallel instead of parallel to the B0 field. And the mechanism for that, of course, is whereas initially there's an imbalance of parallel-oriented spins instead of anti-parallel-oriented spins or up and down spins, this actually gets reversed, and the same proportion of down-oriented spins outweigh the up-oriented spins. So our NMV has actually just flipped from up to down just because of the proportion of up and down oriented spins that compose it. Now this actually is very convenient for regrowth or recovery, which I've got kind of drawn on the right here. This is the same graph as this one. I've just kind of cut out the transverse arm of the axis because regrowth, instead of recovering kind of like getting pulled diagonally back to the axis, it just happens axially. So at time point 1, our NMV is oriented down, and then if we wait an amount of time, it'll be less magnitude still oriented downwards as some of those spins exchange their energy with the surroundings. And then at some other time point, there will actually just be no longitudinal component of the NMV. And then after that, the proportion will, instead of being balanced, switch to being disproportionately up. So our NMV will recover to its full magnitude in the up direction, right? So this is a different recovery trajectory than we've been talking about previously, but it's very convenient because if we consider longitudinal regrowth of magnetization in this scenario, we now have a chart. Instead of previously, I had one from 0 to 100, we've got one from negative 100 to 100, just representing down or up orientations. And our recovery curve looks something like this. Yeah, okay, we'll go with that. But this, again, because T1 times vary by tissue, is dependent upon the tissue that you're looking at. So if this is, say, gray matter in the brain, it's slightly fatty, it has a decent recovery curve, whereas white matter might recover from negative 100 to 100 even faster, probably more pronounced than that, but I'm working with what the space I've given myself. And then if we consider water, water has a much slower T1 recovery time, right? So its curve is going to look something more like this. I'm going to try drawing that again. That one was a little wobbly, not that it matters to anybody. I'm actually going to draw that even more accurately. So these two have reached 100, whereas the water curve probably won't even be there by the amount of time that we're looking at here. Now, perhaps some of you have already noticed there is a very useful time to acquire signal right now. Highlighted in green, if we acquire signal right here, that means we have tons of signal available from gray matter and white matter, and no signal available from water if we tip the longitudinal component back into the transverse plane. So if we just kind of like make a pictogram of what I just said, the magnitude of our longitudinal magnetization will be very high in white matter. It will be also high, but to a lesser extent in gray matter, and it will be pretty much 0 in white matter. And you can do this for other tissues as well. Some of you may have heard of black blood sequences. This is where the same concept applies, but you're considering specifically blood tissue instead of water, although they are fairly similar. And now when we're recording signal from our NMV, we are only really drawing signal from areas of human or body tissue rather than water and CSF and things like that. So you've removed an area of signal that you're not really interested in, and kept those areas dark, which can really help to improve contrast in your image. Do I have a T1 image next? No, I do not. Let me just scroll down to it just to kind of elucidate what I'm talking about. So this is a picture of my brain. And in this picture was collected using the inversion recovery method that I was just talking about. So the reason CSF is dark here in my ventricles is because the inversion time, or the effective echo time of this image was set such that there's no signal available from water tissue. Very, very cool. And that helps to allow us to collect greater contrast in tissue of interest while removing signal we don't want. So that's also used in T1 imaging to make sure that even though we have our steady state NMV that's lower magnitude than it could be, we're really only collecting signal that we care about, and then we're using that signal to outweigh the noise and kind of increasing contrast with surrounding tissue like CSF, which we want to be dark so that we can clearly distinguish the brain. So since we're a little bit short from time, I'm going to kind of just, I think it is kind of useful. I will, well, we'll try. So these techniques are used in modern pulse sequences for T1 imaging. On the GE scanner at the Children's Hospital, this is called the Bravo T1 sequence. And on a Siemens scanner, this is typically, I've never used a Siemens scanner, but this is their MP RAGE technique. Possibly people who are using contemporary Siemens scanners might have their own sequences for steady state T1 imaging, but the MP RAGE is kind of Siemens's proprietary sequence. Now, as I just mentioned, these sequences are proprietary, so I don't have an exact one to show you. This is a pulse sequence diagram of a modified MP RAGE scenario that was published by authors of a clinical paper, which I'm very grateful for. It's nice to have like an actual example of what a pulse sequence might look like. Unfortunately, it's very compressed. So I was going to draw one above, but we're at 12:45, so I figured I would just move on along and give you kind of the main takeaways here. So exact same axes that we've been drawing, the RF pulses, the readout, which is our frequency encoding gradient, that's this one, phase encoding and slice selection as well. Now, you can see this is a steady state sequence because the RF pulse sequence arm here has many, many RF pulses, and these are probably at like, I don't know, 10 degrees or less for flip angles, because that doesn't take very long and can be repeated quite often. So this is a steady state imaging sequence. Another really important thing about it is that we are now acquiring multiple lines of K-space in one TR, right? So you can see that our trajectory, rather than just being, let me just draw this in red, rather than being from left to right in K-space and then resetting and being left to right in K-space, like I've been drawing for simplicity's sake, we're not just collecting one line at a time. We are using this other technique to move through K-space from bottom to top in kind of like a grid scenario, left to right, right to left, using this trajectory that they also handily supplied. Very, very convenient. And this is called the echo-planar imaging trajectory, or EPI. It's also quite common. It's the basis of diffusion-weighted imaging and fMRI as well, as far as I understand, although I'll need to correct that. I was reading about fMRI lately, or yesterday, and some of it may have slipped out of my head. But EPI, very, very common because it allows us to collect information from a whole slice in a compressed time frame. So we can do this sequence to collect 128 or 256 lines of K-space quite quickly. There are some trade-offs, though, because we're not allowing our echo to fully, or our NMV, excuse me, to fully recover every single time that we are collecting an echo. So the echoes are going to be of a lower magnitude. And just because of T2 effects, even though we're using these pulses and frequency encoding gradients to refocus our echo every time, still the lines that are collected at the top or the later part of this trajectory rather than the bottom, the ones at the top are going to be lower in magnitude, just kind of intrinsically, because we've allowed more time for T2 decay to happen. So we need to be able to correct for that as well. Thankfully we can, but this is a trade-off in echoplanar imaging. Is as you are moving through this trajectory, you're losing signal every single time. You need to be really quick and acquire things kind of as fast as possible in order to get a nice looking image of the brain, which we have right here. And this is from an echoplanar imaging Bravo sequence, like what I've just shown you above. So it's the same kind of thing, T1 weighted image. It's just using these steady state and inversion recovery techniques to make sure the signal is predictable and also maximized in our tissue of interest and zeroed out elsewhere so that we can collect signal fast enough to have a sufficient resolution to balance out the noise that is present in our image. Obviously, this image is not as high quality as the T2 weighted image that I showed you previously. That's because this is collected on a 3T scanner, and the resolution is, the voxel size is 0.8 millimeters isotropic. So still quite small if you think about it on the grand scheme of things. These voxels that we're looking at are quite small. Of course, there's tens of thousands of neurons in a voxel like that. But still, you can see quite a bit of detail in the brain. It's just obviously blurry, right? Like this is the effect of noise, like in here. Obviously, there, if I can just kind of highlight the thalamus area in orange, there should be an area that's darker gray there than the white matter beside it, right? So some of that information is meaningful, but not all of it is. There's some blurry grays and whites, and that is noise that we can't avoid. We just need to collect enough signal to outweigh it. Similarly, up here, this is all white matter, but some of it looks almost as gray as the cortex around it just because of noise, right? So this is the SNR. It's the constant battle to maintain resolution and have enough signal to outweigh noise. And that is what informs the choice of scanning parameters in MRI. Thankfully for me and for probably many of you, we don't need to fiddle around with those parameters very much, as there are various skilled physicists that are designing these sequences. But of course, it's very important to understand what those parameters are actually doing for our images. Yeah, and that's everything that I've got before diffusion weighted MRI. We are 10 minutes from noon, so I think I'm going to wrap up there. Apologies if any of you are as excited to talk about diffusion weighted imaging and fMRI as I am, but I guess that'll be the focus of our next and probably final session on December 9th. I've got a feedback form as always, just in case any of you have a minute or so to give me a couple answers to survey questions for essentially my teaching dossier. And as always, happy to answer any questions you guys have. I guess, sorry, I got a little bit ahead of myself. I'll give a session recap here, just so we kind of firm everything up. It feels like we didn't cover quite as much today, but we did it in quite a bit of detail. Hopefully that was interesting to you. So first, we talked about TU2 weighted imaging, pulse sequences. We talked about how they frequently use gradient echo imaging because it's quick and allows us to collect an echo before T2 dephasing has kind of like truncated our signal enough that we don't have much left to image, which is important for SNR. The example that I showed here is line by line acquisition in K-space, which is feasible for gradient echo T2 weighted imaging, although not always used. Something like echoplanar imaging might also be used here to collect slices of the brain or other body of interest more quickly. We talked about how you want to choose your TR and TE for an image to maximize the contrast in whatever parameter that you are interested in. For this example, it's T2 weighting, so we want to find a TR and TE that allow us to maximize differences between tissue in T2, but that'll change, of course, depending on the imaging sequence. We talked about how T2 images generally have water that's very bright, which is very useful for certain sequences. They're very fast and sometimes maybe T2 star weighted instead of T2 weighted because we're not using spin echo. We then took a solid pit stop in the signal to noise ratio, talking about how signal is predictable, it's what we're interested in, whereas noise is unavoidable and random. So the only way that we can kind of cancel out or account for the effect of noise on our image, just to be explicit, we can't cancel out noise. We have to account for the effect of noise in our image because it's omnipresent. No matter what parameters you use in your scanner, we need to collect more signal. And we talked about a few different parameters we can use to maximize signal to counterbalance the effect of noise on our image. Then we moved on to talk about T1 weighted imaging. Oh, sorry about that random zoom. Again, we're choosing our TR and TE to be, short TR, short TE to maximize our differences in longitudinal regrowth between tissues, where fatty tissue regrows more quickly. And that requires us to use multiple pulse sequences or multiple RF pulses per line of acquisition in K-space. So we need two 90-degree pulses in this image that I've shown in order to generate T1 weighted contrast, which might take forever unless we use some techniques to speed up our imaging. Now, the two that I touched on, and rest assured there are many techniques used to speed up MRI imaging. That's essentially like a huge area of contemporary MRI research. The two that I want to talk about, as they are relevant for everybody here, are steady state imaging, where we don't allow our NMV to recover and trust that given enough pulses, we'll eventually reach the steady state where our NMV is always the same amplitude when it's tipped. And that means that we can acquire K-space information that's balanced across the various echoes we collect. That can take a little while. It can take up to like 50 pulses unless we design our flip angles such that we kind of accelerate the time that it takes to reach a steady state. And the second one I want to talk about was the inversion pulse, where we can kind of target our tissues of interest using this 180-degree pulse to isolate signal in tissue we're interested in and zero out signal in tissues like water or blood that we don't really need to collect signal from in terms of this structural imaging. There are other sequences where you really want to look at blood vessels specifically. So you might want to use a different inversion time, TI, another T acronym, to get signal from blood vessels, but not tissue or something like that. That's also possible in something like magnetic resonance angiography, which is MRA. Some really cool images if you look up MRA online. I skipped over actually drawing a T1 imaging sequence in favor of showing you a practical one that was used in clinical research. It's a little bit messy, but it gets across those concepts of steady state imaging and inversion time. That's what this RF pulse is at the start. This is the inversion pulse. And you can see at the bottom here, this is TI, which is the inversion time instead of TE. Because we're requiring more than one echo, TE doesn't really make as much sense anymore unless we consider it in terms of acquiring the center of K-space. So sequences like this are usually quantified by TI instead, which is the amount of time that you wait for your NMV to recover after that inversion pulse. And then the final kind of concept that I brought up that speeds up MRI imaging is echoplanar imaging, which will be relevant next session as well, where we're acquiring multiple lines of K-space in one wiggly waggly trajectory instead of going line by line like I talked about previously. And yeah, just had an example T1 image at the end. Next time we will wrap up with diffusion wave imaging and fMRI. And if anyone has any other topics they'd like me to chat about, feel free to send them my way. But otherwise, thanks for coming today. Hopefully you guys learned something cool.